for solving the linear programming problem. It's a two variable problem, two inequality constraints. They are less than equal to type. So first thing you do is convert them into equality constraints by adding slack variables, and then you can construct the table. Okay, so let me put my slides so that you see how the table look like. Let me see. Yes, let me go to the so here is the table. Can you yeah. So here is the format for the table. Okay, first you write them as equality constraints and then form the table. So you can add slack variable x3 for the first constraint and x4 for the second constraint, right? Like the way we have done it in this problem. And then try to draw this table the way I've got. If there is any difficulty, let me know. Okay.
In this question, is x less than equal to 6 is not a variable?
No, it's not a. It's assumed to be like that. So you don't have to treat it in any way. It's already assumed that x1, x2 should be greater than equal to 0. So you don't treat them as a constraint.
No, x less than equal to 6.
That you have to. Because that's not x1 greater than equal to 0. x1 greater than equal to 0, x2 greater than equal to 0 are conditions that are already factored into LP process. So you don't have to treat them as a separate constraint. But anything else you have to. Okay. Let's put the slide back onto the screen, yeah, so that they can see the whole procedure. Let's keep this on at this slide.
So there are 2 points, infinitive and type. So which point we have to consider?
Minimum, the minimum of all that. And if there is a negative value, you have to ignore that. Ignore the negative, only consider positives, and take the minimum one. Okay, before you make the table, can you draw the feasible region and the optima? Can you solve the way I have solved this graphically here? Why don't you try that first? Okay, so make a sketch of x1, x2 and try to first draw the constraints x1 plus x2 less than equal to 4. So the way to draw the constraint is assume its equality, x1 plus x2 equal to 4, and draw the line. And then take one point, maybe the origin, and see whether it satisfies the constraints. If it satisfies the constraint, then that side is feasible. So see if you can plot that line x1 plus x2 equal to 4. So I can help you do that here. So this is the first constraint, x1 plus x2 equal to 4. Okay, so it cuts the x-axis at 4, y-axis at 4, right? And now to determine which side is feasible, let's take a point on one side. Let's say I take this point, origin. So that is 0 for x1, 0 for x2. Let's substitute it in the equation. So I'll have 0 plus 0, which is 0, and that's less than equal to 4, right? So that satisfies. So this point is feasible. So then you can put there and say dashed lines like this here, showing that the left-hand side is feasible. Same thing you do for the other constraint. So the other constraint will be x1 is minus 1 and x2 is plus 2. This is the other constraints. And then you see, again, if you take origin, I see that that's also feasible. So origin is feasible, so that means I put this way. Okay? And then I have x1 greater than equal to 0 and x2 greater than equal to 0. So this region here inside this polygon is my feasible region. Now in order to find the optimum, I need to draw the contour plot of x1 plus 3x2 equal to, this is the objective function that you have to maximize. So I assume some value. If I assume 3, okay, then this has the equation which cuts x1 at 3 and x2 at 1. So this is the contour line of the objective function with a value 3, because I have used 3 here. Okay. Then if I do it at 6, it will go to 2, it will be a parallel line to that. So this will have a value 6. So as you see that as you go up parallel to this line, your function value is increasing. Since I have to maximize, so I'll keep on doing these things till so this seems to be the optimum point, right? Because you can't go any further. So that's your optimum. This is how you determine in a two-dimensional problem where is the optimum. So now we have to solve these two equations to know what is the coordinate. So this is the intersection of the two constraints. One is x1 plus x2 equal to 4. The other is minus 2x1 plus x2 equal to 2. So solve this problem. So I'll get, if I subtract, I will get 3x1 equal to 2. So x1 is equal to 2 by 3 and x2 will be 10 by 3. So this is roughly 3.33 and this is 0.67. So that's my optima, 2 by 3 and 10 by 3. Okay. You can also compute the function value at that point. So function value will be x1 plus 3x2. So 2 by 3 plus 10. So 32 by 3. So this is the solution graphically. But now let's see whether we can get that point by the simplex method.
How to get the contour line, please?
Contour line is, you have the objective function which is this, right? Now you assume some value, because the right hand side, there is no right hand side for objective function. So say it's 3. So now you can draw the line x1 plus 3x2 equal to 3. You can draw the line like you have drawn the constraint. So here is that line I have drawn. The fact that I have assumed 3, that means any point here on the line will have a value 3. So the function value for that contour line is 3. Now if I increase it to 6, you can draw it again. If I do 6, it will be this line. So any point on that line will be 6. So now you notice that 3 to 6 to 12. So this is how it's going to increase. So it's increasing in this direction. Okay. So this will be the last point that you can get.
Rather than going to the corner point.
Yeah, it has to be the corner point. You cannot go any further up, right? Because there is no supporting point. Your feasible region is inside. So this will be the last point that gives you the highest value of f. And that is what you've computed, 10.66. This will be 10.67. Okay. So have you drawn the first table? Okay. So what point does it represent? What are the basic variables? x3 and x4. x3 and x4 are basic variable. So this table represents which point? Origin. So this is the origin that it represents. Mark that point as A. And on the table, you can go and mark like I have done here. You can mark it as point A, like we have done here, right? This point A over here, and point mark A. All right. Now, have you computed del FQ? So, which one has the highest value? X3? X2 again is the highest? Okay, and then minimum ratio rule? X4 will go out. So, very similar to this problem, right? Okay, so let's bring in X2 and make the second table. Now, unfortunately, you cannot erase the table. You have to make another table. So, make it. It's a little bit of work, but once you do it few times, you understand it. Which one? This one? CB. CB is the coefficient of each of these in the objective function, right? Yeah. So those are 0, 0 for x3, x4. Right. So when you bring in x2, bring the coefficient of x2 here. Okay? And now x2 coefficient here has to be 1 and this one should be 0. On the first equation, the corresponding x2's value should be 0. So do you have it that way? So then you have to do some row manipulation like the way we said. You multiply the pivot row, that means the x2 row, by something and subtract from it so that this becomes 0. Okay? Is that clear to everybody? Okay, let me try to do the first one at least. x1, x2, x3, x4. And we've got 1, 3, 0, 0. So did everybody got this? Yeah. Okay, what are the basic variables? All the basic variables take the value on the right hand side. All non-basic variables take a value 0. So in this table, x1 and x2 are non-basic variables, right? Because basic, here I wrote basic, they are x3 and x4. So x3's value is 4, x4 value is 2, x1 is 0, x2 is 0 automatically. So it's by default all non-basics are 0. Okay? Has everyone got this first table? Yeah? Yeah. How means you have to add x3 to first constraint to make it an equality constraint, right? Where do you get your x3? Where did you put your x3? Have you got x3? Where did you put your variable x3? So you have to go a little back. I think you are lost right in the beginning. You've got a constraint that says x1 plus x2 is less than equal to 4. How are you converting it to an equality constraint? No, let him answer. How are you doing it? You will have to add a slack variable, right? and x3 is that slack variable. So x1 plus x2 plus x3 equal to 4. That's how you get x3 there. Similarly, the second one you are adding x4. Okay, so that's how you get it.
x1 2 by 3, x2 10 by 3.
Yep, 2 by 3 and 10 by 3. That's what it's supposed to be. Okay, so let me draw the next one so that some of you couldn't do can see how to do it. x2, x3, x4. These are automatic. 1, 3, 0, 0. Okay, now basic here. So I decided x3 will remain x3, x4 will be replaced by x2. So I'll immediately bring coefficient 3 here, 0 here, and now I'm going to write this. So I have to make sure. So x3 is not. So this one x2 here, I have to make. This is the pivoting one, so I have to keep that, and that is 1. So I just keep it because I want to make this 1. So this will remain the same. Now the top one, I have to make this one 0, 1, 0. So the way I do this, I subtract the second one from the first one. Then I get 0 over there. So 1 minus minus 2, which is 3. 1 minus 1, 0. 1 minus 0, 1. 0 minus 1, minus 1. 4 minus 2, 2. Okay? So now that I have got this, you see x2 is in row echelon form, x3 is in row echelon form, but neither x4 nor x1, but those are basic. So now let's compute del FQ. 1 minus 0 minus minus plus 6. So you get 7, right? 3 minus 0 minus 3, 0. 0 minus 0 minus 0, 0. 0 minus 0 minus 3. So minus 3. So this is the one that is highest. Now we do 2 by 3, and here we will do 2 by minus 2. So minus have to be ignored, as I said. So 2 by 3 is the one. So this is my pivot element. So what is this point representing? Point B. And what is that? x1 is still 0, and x2 is 2. So what is that point? 0, 2, this point. So this is my point B. Okay? So now you bring x1 in place of x3 and do one more step, and that should be the optimum, because it looks like it's going to go to that one next. So it moved this way, and then it's going to move that way, and another iteration you will get it. Okay? So the final solution should be x1 is 2 by 3, x2 is 10 by 3. You are getting that over there? Are you getting? Or not yet there? Not from here. You have to do one more step, because we haven't converged yet. Because this is all, not all are negative or 0. We've got one positive, so you have to do one more step. Can you do that step yourself? Come back. It happens. It just goes through that process. It depends on how it's moving. Yeah. For higher number of variables, that chance is less, but it can happen as well. No, why? x3 is replaced by x1. So we've chosen x1 to come here, and this says x3 will go away. So you have to make 3, 1 in the next step, dividing everything by 3, and then this one 0. How will you make that one 0? If this is 1 already, yeah, so multiply this by minus 2 or 2 and add with this. So once you divide this by 3, then this has become 1. Now you multiply the whole row by 2 and add with this one and write it here. Then you will get 0 here. Okay? Is that clear? Yeah, then you have to find delta FQ. What are you saying? Yeah. Yeah, then you only have to do delta FQ. But first you have to do row operation. First row operation and then delta FQ. And then if you see all delta FQs are negative or 0, then you stop the process because you found the optima. Okay? Right. Yeah, 2 by 3 and 2 by minus 2 because this is my pivot column now. So 2 by 3 is this and 2 by minus 2 is this. So negative we don't take because negative means I can keep on increasing that variable x1 and it's not going to make my x2 0 or anything. So negative is fine. Negative you just ignore. And only look at the positives and the one having the smallest value. So in this case there's only one positive. So that's the one has to be chosen. Any question at the back? Anybody has? Because you need to understand this well. Yeah, go ahead. Okay, 1 minus 0 times 3 minus 3 times minus 2. So 1 minus 0 times 3 minus 3 times minus 2. 1 minus 0 times 3 minus 3 times minus 2. So that if you calculate, it's going to be 7. Similarly, 3 minus 0 times 0 minus 3 times 1 is going to be 0. That's the formula for del FQ. That's why you have the table. So everything is in front of you. You can do all these operations. Everybody is done? Or some more time is needed at the back? Please say yes or no. Okay, so then let's move to the next question. Make sure that you plotted it and showed every point what's happening. Okay. Okay, next question is now there is a greater than equal to constraint. So what are you going to do? We're going to use the two-step method, two-phase method, dual phase method. First phase, we will just minimize the artificial variable. So first rewrite the constraints. Rewrite the constraints by adding slack variables and artificial variables. So what happens to the first variable, first constraint, x1 plus x2 plus x3 plus x4. Sorry, that's the one that is greater than. So minus x4 plus x5 equal to 1. Then we have x1 plus 3x2 plus 5x3 plus x6 equal to 6. That's it. Is that okay? So now let's form the table. So what are the basic variables here? x1? No. No, how many basic variables there would be? No. Wait. How many basic variables there would be? 2. The number of basic variable is same as the number of constraints. Because every basic variable has to have a supporting constraint. So what are these two variables? x5 and x6. Why x4? You cannot have negative. You cannot have minus 1 as the coefficient of the basic variable. It has to be plus 1. And that should not be present in the other constraints. So x4 is not option for basic variable. That's why we add the artificial variable x5. x5 and x6. Okay, so write down the equation. Okay, and what is the objective function? So let's first write x1, x2, x3, x4, x5, and x6. And now what are we minimizing or maximizing here? We are maximizing what? We are doing the dual phase now. Minus x5, good. Everybody agrees? Why? Because x5 is the artificial variable and we want to get rid of it. So we are saying we are going to minimize x5 or maximize minus x5 with the condition that x5 greater than equal to 0. So it should eventually come to 0. Okay. So now if this is the objective function, what are the coefficients? 0, 0, 0, 0, minus 1, 0. Okay. Now let's write the basic here. So as we discussed, for the first constraint we get x5, second constraint we get x6. All right. Now let's write the constraint. So first one is 1, 1, 1, minus 1, 1, 0, 1. Second one is 1, 3, 5, 0, 0, 1, 6. Okay. Here the coefficient of x5 is minus 1, coefficient of x6 is 0. Everybody has written that and understood? Okay. Now let's compute del fq. 0 minus plus 1, 0 minus plus 1, 0 minus plus 1, here minus 1 means plus 1, 0 minus minus 1, minus 1, minus plus 1, 0. This two will be 0 anyway because they are basic. This will be 0. Okay, now I've got 3 of them with 1. So we can take any one of them at random. Okay, which one you'd like? Choose anything so that there is some differences that we see. I'm not going to tell you that. Choose whatever. Any one of them you choose so that we have some differences. Okay, whatever you have chosen, then you go to this side. For example, if you choose the middle one here, but you don't have to, as I said, you can choose any two. So now I go 1 by 1 equal to 1, and here I go 6 by 3 equal to 2. So now this is the smallest one. So this says x5 will get replaced with x1. So this is my pivot element. Sorry, not that one, this one. x2. Okay. Is it okay for you? All right. So then you can write the next step because we still haven't conversed. Draw the next table. So in the next table, we have to make, this one is already 1. This one I have to make 0. So what do I do? Again, do the same thing.
Price of x5.
0, 0, 0, 0, minus 1, 0. So this one I convert it to x2. This one still remains as x6. And then here I've got 0, 0. Okay. Now this one is 1. 1. This one I have to make 0, x2. So what I do, I multiply the top one by 3 and subtract from the second one. So 1 minus 1 minus 3, so it's minus 2. 3 minus 3, 0. 5 minus 3, 2. 0 minus minus 3 plus 3. Minus 3. 1, 3. Okay. Now let's compute del fq. 0 here, 0 here, 0 here, 0 here. Minus 1, 0, 0 here. Sorry, minus 1 and 0 here. Okay. Yes. How to get this? Okay, so you have to make this one over here 0, right? How will you make it? How will you make this 0? So you multiply the top one by 3 and subtract from the second row. That way you'll make this 0. So 1 minus 3 times 1, you get minus 2. Got it? Okay, now it's the optimum because nothing is greater than or equal to greater than 0. So this is the optimum. So now that it's the optimum, we have to then move to the second phase. And one variable I can eliminate, which is that the artificial variable. We don't need anymore. So x5. So this one I can cut. I don't need it anymore. And I can continue from it. But now I have to write the original objective function now. So which means the c values are going to change. So make another table without the x5 and continue. So before you do that, let's see what we have done in that process. So if you now write the equation from this, what is this first condition telling me if I take out the x5? It's telling me x1 plus x2 plus x3 minus x4 is equal to 1. And the second one, 2x1 plus 2x3 plus 3x4 plus x6 equal to 3. Okay. Now look at these two equations and what you have gotten. Can you obtain these two from that equation? Is it possible to get from here to there? So it looks like x5 is 0. So if I put x5 0, I get the first one. But what about this one? This one got somewhat manipulated, right? So yeah, if we try to eliminate x2 from the second equation, what I would do, I would substitute the second equation. So substitute second equation by, let's say this is equation 1, equation 2. If I do this, 2 minus 3 times 1, I get an equation and I substitute that with this. You will get back that equation. And put x5 equal to 0 in that. You will get back this equation. So this is exactly what we have manipulated here, so that we have a basic variable right here. We have a basic variable right here. Right? But from these two, I mean, if I didn't have x5, there is no way for me to get a basic variable set, because here x1's coefficient is 1, but so is here. It's not 0 here. x2 coefficient is 1, but here it's not 0. So I cannot find it. But this first manipulation is done through the simplex method. So I get two of the variables having one coefficient in one of them and 0 in the other. So that's what this is done. So now that I've got this equation, which is equivalent to this equation, I don't need x5, right? So I can start from here with my original objective function. So can you now write the second phase? What will be the second phase? So we've got x1, x2, x3, x4, and x6. And what is the objective function? 1, 2, 0, all zeros. Oh, sorry, this is x3, 1, 0, 2. You're right, 1, 0, 2. Okay. So, and copy the same thing from the previous table here. And here I had x2 and x6, and now we have 0, x6, 0. Del FQ. Okay. Okay, so let's find out what is del FQ. 1 minus 0, 1, 0, 2, 0, 0. So obviously x3 is that thing, and here we have 1 by 1, which is 1, 3 by 2, which is 1.5, so this is smaller. So x2 will get replaced with x3, right? x2 will get replaced with x3. So can you do that? So you have to now make this 2 equal to 0. So the way to do this is multiply the top one by 2, subtract from the second one. While you do that, let me try to find the solution through MATLAB and see what is the solution, because it's a 3-dimensional problem. It will be difficult to do by graphical means. So f is equal to 1, 0, 2. Maximizing, we'll do that. A equal to 1, 1, 1, 1, 3, 5. That's it. wait a second, there is some issue with my problem formulation. It's giving me some absurd value, infinite value. Wait a second, what did I do wrong? F, I said, want it to be minimized or maximized? 1 second. No, that's also not working. So this problem is not defined actually, the way I've done it. I wonder whether, just let me put some arbitrary thing here. See what happens. No, still getting very large value. 1, 6, -1. Minimize is giving me these values. It's reducing. Let's put this 0. What happens? These are very large values. Why is that? Maybe I need one more constraint for this, but let me. This is less than 6. Maximize. No, minimum ratio negative you have to ignore. Okay, what's happening in this problem? Let me see why this is having issues. So we have one constraint that says 1, 1, 1, and top side is feasible, and then this one makes it at 6 for x1, x2, x3. Other one is at 2 over here, and 1.2 over there. So the region in between is feasible. Fine. Now if I'm trying to maximize now x3, I should get the result. But why is it not coming? Let me see. Maximizing x3 means 0, 0. So yeah, maximize 0, maximize x3. Okay, it should work. Let me see if I got this right. -1, -1, -1, and then it should be -1 over here, right? So that's fine. And then next one, 1, 3, 5 is, I put 6. I should put 6 here, but that should not. And maximize f. So my minimize -1.
Constants we got minus sign, sir. That's why. Constant we got minus sign, sir. That's why. Equal to.
No, where do you get minus?
Next iteration I got, sir.
You got minus? Yeah. No, I have to see. Looks like this problem is not defined properly. But why? Because I have. Lin prog FAB, yeah, FAB. Why is it coming so large? Okay, I wonder. No, 0, 0 is not inclusive. It is probably that we have to supply the lower bound. It probably doesn't, the MATLAB doesn't assume that x size has to be less than 0. Let me just check. Does it say anywhere? It doesn't say anywhere. Okay, so maybe I need to supply the LB. Let's see what happens. So I go to MATLAB here. Okay, so where is my screen here? Okay, so now I'm going to say here lower bound equal to 0, 0, 0. Okay, and now I'm going to come here, and I think there is A equivalent, then B equivalent, then LB. Okay, now let's see what happens. Yeah, now we get. So I think the MATLAB code doesn't assume that all x size has to be greater than equal to 0. So that's why it's a kind of open space, and it's going to plus infinity. Okay, but I think the problem I gave you is probably fine. Let me check. So you're maximizing. So this was 1, minus 1, and this one minus 3, right? Minus 2. And then rest all are fine. Yeah. Minus 1, minus 2. Let's see. Yes. So the result would be 6, 0, 0. Ultimate result will be 6, 0, 0. And the function value is minus 6, plus 6. Are you getting that? Have you gone all the way? So the problem is fine. You can continue with it. It's just that when you're using MATLAB, you have to supply the lower bound, so it doesn't violate, doesn't go to the negative side.
Sir, during row manipulation, pivoted the point that it is required to be unity.
1. Yes, has to be 1. So have you got the second table out of this? Okay, so what has become now? So x1 has become the basic, right? Okay, and then next table, what is becoming basic? Now x3 comes in. Okay, eventually x1 has to come in. So this table tells me we are at 1. So next table, what is the basic again? x1, no, x3, x3, x3 becomes how much? x3 becomes 1. x3 2, and x1 x2 0. No, there is no such point. You may have done something wrong. Let's see. So x1, x2, x3, x4, x5, x6. We have still here 1. So we are maximizing, right? So 1, 0, 2, 0, 0. Okay, so I've got that one 1, so I can keep it. Minus 1, 0. This one I have to make 0, so this corresponds to now x3, which will be 2, and this remains as x6, this will be 0. Okay, so now I have to make x3, this one 0. So I will multiply the first row by 2 and subtract from the second. So minus 2, minus 2, minus 4. 0 minus 2, 0. 3 minus minus 2, 5. 1. And 3 minus 2, 1. Okay? All right. So let's compute now del FQ. 1 minus 2 minus 1. 0 minus 2. 2 minus 2. 0 minus plus 2. 0, 0. Okay, so I have one of them plus 2. Okay, so now x, this is 1 by minus 1, which is minus 1. I cannot take it. And then 1 by 5, which is 0.2. This one has to be taken. So this is, anything wrong?
In the first second table, we have positive 2 at x6 where we have put minus 4. In the previous table, that was 2 positive 2.
Is that right? Which one? Is it this one? From the phase 1. Phase 1 or phase 2? Phase 1. Okay. What are you saying? Which part? The second table. x6 should be? This one should be 2. Okay. How did we get that? We were multiplying the first one by 3, subtracting from second. So 1 minus 3 times 0 should be 1. Check that. Seems to be correct. Okay. All right. So if I go back to this is phase 2. Phase 2 and table 1. So here the x1 value is 0, x2 value is 1, and x3 value is 0. Okay. Now in this table we've got 0, 0, x3 is 1. Yeah, so that's what I was asking, but you're telling me 2. I don't know how you're telling me 2. So if I get to this plot, okay, so this is my first table point A, which was this. And now we move to this. So we came this way, we moved there. This is my point B, which is this table B, point B. Okay, I moved to the 0, 0, 1. And now x4 has to be replaced with x6. So again write that x1, x2, x3, x4, x6. 1, 0, 2, 0, 0. x3 remains as x3. x6 will be replaced by x4. Here x3 coefficient is 2. This is 0. Okay, so now I have to make 5, 1. How do I make 5, 1? By dividing everything by 5. So I have minus 4 by 5, minus 2 by 5, 0, 1. Sorry, this is 1. This is x3, which is 0. x2 is minus 2 by 5. And x6 is 1 by 5. And this will also be 1 by 5. Okay, now this minus 1 has to be made 0. How do I do that? I simply add this column with that first column. I can do that. So if I add, then this will be 0. So let's see. Minus 4 by 5 plus 1. It will be 1 by 5. Minus 2 by 5 plus 1. 3 by 5. 0 plus 1. 1. 1 minus 1. 0. 1/5 plus 0. 1/5. And 1/5 plus 1, which is 6 by 5. Everybody got it? Okay, now del FQ is 1 minus 2 by 5, which is 3 by 5. 0 minus minus 6 by 5. 2 minus 0, 0. This one minus 2 by 5. So I have still 1 that needs to be looked at. And then this is 6 by 5 by 1 by 5, which is 6. And this is negative, so I don't worry about it. So this is the one. So now it says x3 will be replaced by x1. Okay? And what point is this? x1 is still 0. x2 is still 0. x3 is 6 by 5, 1.2. And you see, I am getting now to this point. This is my point C. I moved here. Okay? Up there. So in between the two planes is my feasible region. So I came to this, then moved there, and then moved up. And this is my optima actually. C is my optima. So you'll see that that's going to happen. Okay, so this is clear. Now I move to another page. This is point C. But if that's the optima, I should have obtained it, right? Why do I have 3 by 5?
Should have been negative.
Oh, no. This is x3. I'm sorry. Oh, yeah, x3. Oh, no. This is the optima for the revised problem that I was doing. Okay, that's not the optima yet. Okay, let's see what happens. So we need one more. So we go x1, x2, x3, x4, x6. And then I've got 1, 0, 2, 0, 0. And then x3 remains as x3. Sorry, this one becomes x1 and x4 remains as x4. So 1, 0. Okay, so my pivot element is that, so it's 1/5. So I need to multiply it by 5. So I get 1, 3, 5, 0, 1, and 6. Okay, now minus 4 by 5 has to be made 0. How do I do that? So I have to multiply the first one. Yeah, add it to that. So for this becomes 0. So 3 times 4 by 5 minus 2 by 5. So 12 by 5 minus 10 by 2. Okay. Then we have 5 I multiplied by 4 by 5, which is 4. And I add to 0. So I get 4. All right. And then 0, it will be 1. The next one, 1 I multiplied by 4 by 5. So 4 by 5 plus 1 by 5, which is 1. And this one, 6 times 4 by 5 plus 6 by 5. So 24 plus 36. Okay? Okay? So now let's compute del FQ. 0 minus 3, 2 minus 3, 0, 0. So everything is negative. So this will be the optimum, right? Now what is the value here? What is the point here? 6, 0, 0. Okay. So if I look at my plot, let me see what I did, because this one I changed my problem and that's what I was looking at. So here it is x1 plus 2x3. So I have an inclined thing, x1 plus 2x3. So these 3 corner points we have to check. So what we got is now this is the point D we got right now. Okay, 6, 0, 0. What is the function value here? 6, 0, 0, 6. What is this point? 0, 2, 0. What is the function value? 0. And this is 1.2, 0, 0. Function value is 1.2. So this is the optimum. And that's what we got. Right? Is that clear? So we needed 1, 2, 3, 4. So it went this way, that way, went up, and this. It did not come from here to there. So this was the question that you are asking here, right? That whether it takes the least number of steps. But you see, in this case, it started from here because this origin wasn't feasible. That's why we needed to do the dual phase. But we started from here. Instead of going straight from here to there, it actually went there, went up, and then came back. Okay? So, unless we have done any mistake. I don't know. Maybe we have done a mistake. I don't know. But, yeah, 3 iterations to get there. happened. But I think there was an issue with the three beings 1, right? 1, 1, 1, remember? At the very first case. Where was that? We had 1, 1, 1 here, right? So we choose x2, and maybe that was not a good choice.
I got it in one equation only, but I choose x4 to enter.
Yeah, so maybe some other, if you had chosen, there was a shortcut. Yeah, so we were unlucky, you were lucky that way. Yeah. Okay, so everything has a reason why it works. Yeah.
I was selected x1, it became order ranges.
You still working on it? Okay. Good luck. Yeah, you have a question?
First case is x5, which is the artificial variable. If it is not getting eliminated, then what?
It should, because you see, you are minimizing x5 and x5 greater than equal to 0. What is the solution? You want x5 to be 0 or more, but you want to minimize x5, so that it has to be 0. The optimal solution has to be 0. It will come there. Okay. As soon as the x5 goes away from the basic set, if x5 becomes non-basic, its value is 0, and then it will stop. And it probably happens in one iteration. Because you see, x5 was basic here, that's why it has a value 1 to start with. Next time, x5 is gone, replaced by x2. As soon as x5 is gone from basic, its value is 0 because it becomes non-basic. Then you will stop because you are minimizing x5. So it will always happen. Right?
Maybe if we are having delta f same for two variables, now we are basically
Yeah, now we're taking at random.
But what we can do is we can compare the difference between the ratios for both of the variables.
I cannot tell whether this will work in all problems. So you need to investigate a little further whether there's something else can be done. Because this effect you don't know unless you have followed that after some time, and then you know you are in the wrong path or right path. At this point, you don't have that much information. Can you get it from these differences or whatever? I don't know whether this can be a theory or this is just a chance. So if you want to suggest something, you have to make sure that you have theoretical support. But definitely, these are some things you should be looking for. That's missing in the literature. Can you say something more about that? So that way you can. So I have taken 2, 4, 5 steps to get there. And if you're choosing x4, then you've gone in 1 step. So that's a big savings in time. So if you can come up with some theory, that's great. Okay? Everybody got it? All right. So then let's do the last problem. Exercise 4, the first problem. It's an integer linear program. We are not going to be using this tabular method now. We are going to be using graphs to solve every LP. Okay, sorry, I have changed the problem because this is the same problem as I have in the notes. So let's do some other problem. I have to show you that problem. Need to open it up. X4 PDF. Okay, here is the problem. Can you see it, all of you? Or I do some plus. Okay. Write it down, please, first. Maximize 0.5 x1 plus x2 subject to, there are 2 constraints, 2x1 plus 3x2 less than equal to 90, and the absolute value of x2 minus x1 is less than equal to 10. x1, x2 greater than equal to 0, and both are integers. All right? Okay, only hint I'm going to give you here is the absolute value of x2 minus x1, that second constraint. How do you handle it? There will be 2 constraints out of it. Which is the first constraint? So if I tell you x mod x is greater than or less than here, right? So less than equal to 1, What are the two things you can write? So x goes between -1 to 1, right? So -1 to 1, x lies here. So how do I write it as two constraints? Take out the mod. X less than equal to 1 or x greater than equal to -1. Okay, everybody agrees x greater than equal to -1, less than equal to 1, two constraints. So now you have mod x2 minus x1 less than equal to 10. What are the two constraints?
x2 minus x1 is less than equal to 10, x2 minus x1 greater than equal to
Minus 10. Is that okay? So x2 minus x1 less than equal to 10, x2 minus x1 greater than equal to -10. Okay, so replace that constraint with these two constraints. So second constraint will be replaced by two constraints. First constraint, so there are three constraints in the problem. Okay, now can you make a plot of this function first, because we are not going to use the simplex method because it's too tedious to solve every problem. Now first thing is to assume both x1 x2 are non-integer. It can take any real number, so it's like an LP. So now can you plot it, x1 versus x2? So plot like this, x1 x2. You only have to plot the first quadrant. Make a sketch. So how do you plot a straight line like 2x1 plus 3x2 equal to 90? You can always put the lines this way, x1 by a plus x2 by b is equal to 1. If you have a straight line like this, then it cuts here at a and it cuts the y-axis at b. So can you write the first equation in this format? So what is a? 45, 90 by 2, and b 30. So go to a sketch now like this. So roughly, so you have 45 here and 30 is little smaller, so put little small and draw a line like this. 45, 30, right? And then which side is feasible? Origin, because if you put origin, it satisfies on the constraint. So put it dash like this, saying that the origin is feasible. This side is feasible. Then take this constraint, x2 minus x1 less than equal to 10. What is that line? Minus 10 for x1 and x2 plus 10. So you've got 2 points. Now you can join the line. Which side is feasible? Is origin feasible? Origin is feasible. So I will put this way. Okay, so this equation is x2 minus x1 is less than 10. Now let's do the last one. x2 minus x1 greater than equal to minus 10. What are the intercepts?
x1 plus 10,
x1 plus 10,
x2
minus 10. So this will be a parallel line to that one, right? And which side is feasible? If you put origin, is it feasible? No? Origin is not feasible? Think about it. Why is not origin feasible? No. How do you see whether a constraint is feasible at a point? Does it satisfy the constraint? What is the constraint? x2 minus x1 is greater than equal to minus 10. If I put the origin, that means 0, 0. We have 0 here. Does it satisfy? 0 is not greater than minus 10? I'm learning a lot of new things here. Okay. 0 is greater than minus 10, right? So 0 origin is feasible. Okay. So now what is and then we also have x1 and x2 all in the first quadrant. So we have this region here, as you see, is the feasible region. Okay. Now how do we get the optima? We got the feasible region, but how do you get the optima? One of the corner points, but which one? We have to draw the contour. So 0.5 x1 plus x2. Let's assume it to be 1. If we assume it to be 1, how is that line? So again, by the intercept, what is the intercept of x1 for this line? 2 and 0, 2 and 1. So 2 here and 1 here, so like this. So 10 here and then 5 here, right, like this. So like this it goes, and then it's going to increase, right? Am I have to maximize? Yeah. So slope like this. So it seems to be either this or that, right? It's not very clear the way I've drawn. So you have to just check then which one it is. So what is the intersection here and what is the intersection here? Let's find that. Someone find that and tell me. Looks to me the top one is going to be, yeah. So what's that value? Because we need to solve it. So solve the equation x2 minus x1 equal to 10 with the other equation 2x1 plus 3x2 equal to 90. We can check. We can check. Whenever there is doubt, you should check. But then why don't you compute the intersections? No, graphically to me this one. Because this one is going with a lower value. This one is a higher value. So the maximum you can go in that direction.
The slope of this one is lesser.
Yeah, slope of this is what? This is 2 by 3. Minus 2 by 3. And the slope of this is 0.5. Minus 0.5. So minus 0.5 is bigger than minus 0.67. Huh?
12 and 20. 22 and 12.
Oh, I'm sorry. No. Please make a change. I forgot to change. 90 should be 91. Otherwise, we get solution at the first attempt because it's integer solution. Make it 91, okay, instead of 90. So that doesn't change too many things. It's just your picture will become little bit 45 point something and 30 point something. Make that 91, please. 90 to 91. Okay. So then you have to recompute this because I want it to be a non-integer. That's why 90 doesn't make it non-integer. Yes, that's the one. 12.2, 22.2. Let me fix that by that time. Okay. This is the revised problem. Okay. 12.2 and 22.2, right? So that becomes your solution to LP1. Is it not? So let me put it this way here and you solve and tell me. So this is your LP1, 12.2 and 22.2. And what's the function value? 28.3. Okay. Now we need to branch because none of them is an integer solution. They are 12.2, not 12 or 22. So we can decide which way to branch. Let's say we all decide we are going to branch on x2. So what should be a constant here? x2 less than equal to what? 22. And x2 greater than equal to 23. So now let's add that constraint and solve it again. Now that I have got this picture, it will be a little easier to solve, right? So 22.2 is here. Actually, I made a picture here. Let me see if I can reproduce it. Let me quickly plot it. I don't think I saved it. So, okay, this one is the first one. And what are the problem again? And okay, 91 minus 2, this seems to be another one. And then I should have one with the x minus 10, I think. Yeah, that one. Okay, now I have to switch to the positive side. X range. This is a software I use for doing all these calculations. 45, and then y range, let's make it 45 as well. We set the size to be square so we can see it in scale. Okay, so this is what we got before, right? So this inside region is feasible. This region is feasible, and the intersection of these two was our, yeah. So now I'm going to make a grid. Okay, set x sticks at 1, 0, 1, comma. Instead of going all the way to what are we are going to the, I think things are interesting here, right? So I'm going to say 5 to about 20, okay, and here 10 to 25. Okay, so we're going to say 5 to 5, comma 1, comma 20, and y ticks we are going to do what did I say, 10, 1 to 25. Okay, and then set grid, and then replot. Okay, now it's too much. So yeah, so I need to set the x range also. Maybe that will work out. X range we said 5 to 20, and y range 10 to 25. 10 to 25. Okay. Yes. Now I can see. So every intersection of the lines is an integer point, right? Those are only allowed. So we are here, which is not an integer point, and that's what we got, 12.2 and 22.2. Now when I add this constraint here, which is x2 less than equal to 22. So where is x2? x2 is here. So imagine there is a line here. Okay, x2 less than equal to 22. So all the region below, so this is the feasible region, below that line is feasible. And then we have the slope, which was like, if you go 2 this way, you go 1 up. So that kind of a slope. Which point? So I need to blow up over here to see that. But you see, this is the line I'm going. So it looks like this is the point, right? Do you see that? Or shall I blow up even further? Let's see if I can do this. Okay. So here is the point. Because I have a, this when I add x2 less than equal to 22, when I add, all the points below the 22 line is feasible now. Okay? Because that's how I have divided it. And now I have the objective function, which is as a slope, which is like this. If you go 2 this way, you go up by 1. So looks like this corner point, this point that I've put here, will be the result of that. So how do I find this point? To the green line equation, I will set x2 equal to 22 and solve and find what is x1. So the green line is that inclined line. 2x1 plus what is that? 2x1 plus 3x2 is equal to 91. So put x2 equal to 22 and find x1. 12.5 is what I am getting also. x2 is 22. Okay? So that is that point, 12.5, you see. Where is the range here? Okay. So you don't see the level, but it's 12.5 and 22. But that's also not my solution, right? But let's write it. So what we get here is 12.5, comma 22. And what is the function value? That's 28.25. Okay. Now let's do LP3. What will be LP3? To the original problem, I add a constraint that says x2 should be greater than or equal to 23. So here is 23. Above that line, above this 23 line, is there anything feasible? All the feasible was here. So there is no feasible solution. So you fathom it and say here, because it's infeasible. We don't have to continue further branching from there. But LP2 is still not an integer solution. So I can still branch on it. So which variable is not integer? x1. So I have to branch on x1. So what will be x1 less than or equal to? 12. And this one, x1 greater than or equal to? 13. Okay. So let's call this now LP4. and we'll call that LP5. So what's the solution for LP4? Now let me go and then make that line, if I see if I can. So replot, I open up this is a little primitive software, but let me. So what is that value? That was 22, right? So I'll do I guess maybe I can do this. Replot 22. I think this should do. Yeah. So that was the line. Okay. So this line below is now feasible for LP2 and this region here. Okay. Now x1 has to be less than or equal to 12. I need to put one more line. Now where is my 12 here? What's happening here? So let me didn't set the range properly. X range, Y range. I did 10 to 25. Why everything else is coming? 10 to 25. Yep. Y range. Replot. Replot. This is weird. This is weird. Okay. Set Y range 10 to 25. Okay, back there. Okay, now I see them. Okay, so x1 less than or equal to 12. So here is 12, x1. Less than or equal to 12 means this side. So I've got from here on and down here, this side. Okay? So I can try to plot this now. VAA. So 12, 0, and 12, let's say 50. Oi, why so many? Okay, I delete it. Twelve, 0, 12, 50. So I'm going to draw a line with these 2 points actually. So replot AA. It didn't draw the line. Okay, I'll do 12, 10 to 12, 25. 12, 10 to 12, 12, 20, 25. Okay, now it should be able to draw. Still not drawing it. 12, 10 and 12, 25. It's drawing something, but right there. Okay, let me check again. 12, 10 to 12, 25. Okay, yeah, I'm right here. Oh, okay. It did some with point. I have to say with line. With line. Okay. So now, so what is the feasible region now? This part. Everyone agrees? Yes. This is the part. So now if you minimize that function, which point you will get? Is this point, right? Because you are going up with this kind of slope and this is the point. What is that point? That will be when I've set x1 equal to 12 and intersect with the red line. What is the red line? Is the first constraint, which is x2 minus x1 is equal to 10. Now we are going to set x1 equal to 12. So what is x2? 22. So this solution is 12, 22 and the function value is 28. Now do I continue further from this? No, because this is an integer solution. So fathom it. Okay, now I'm left with L5, LP5. What is LP5? It's the LP2 problem, which is this pink line. And now I'm going to say x1 greater than or equal to 13. So I'm going to make another file. So we see it called BB. And it was 13 now, and 10, and 13, and 25. So it's going to draw a vertical line now. Replot BB with line. Okay, so now I've got this line onwards, this side. You see, in between, all solutions are not feasible. But this line, all the points on this line is covered by this way, and all the points on this line are covered for LP4. So this is LP5. Okay, so here is my region. Here is my region. Okay, so which point is the best point? Again, you have a slope of 2:1, right? Is this point, is it not? This point. So how do you find that point? Again, the constraint is this green constraint, which is 2x1 plus 3x2 equal to 91. All right. And then what is the x1 value? 13. So what should be x2? 91 minus 26 by 3. How much is that? It's 21.67. Okay. So write that. 13, 21.67. What is the function value? 28.17. Shall I continue further?
We need to maximize. So
We are maximizing. So we have an integer solution already at 28. And this is 28.17. So if I go down, it's going to only get worse. That means it's going to be smaller than 28.17. But there is still a chance that there is something between 28 and 28.17. So I cannot fathom it. Oh, so we have to do further, right? So let's continue. Okay. So how do we now split?
x2.
X2 should be less than 21 and x2 should be greater than 22. Call this LP6 and call this LP7. Hopefully we will terminate here. Okay, let's see. So how do we get LP6 now? Go back to LP5. So LP5 is this. Now we are saying x2 should be less than 21. So here is 21. So I can add now replot 21. Okay, so I've got this line, this green line, and this over here. So which point is optimum now? This is the feasible region now. This point. So that means I will set my x2 to be 21 and green one I will use. So this one I will use, but now set x2 equal to 21. So what is x1? 14. So this is 14 and 21. What's the f? 28. Now that's the integer solution, I can fathom it. You see, I have not improved from it. It's the same solution, same function value I got, but two different solutions. What about LP7? Will be x2 greater than 22. So this was my original one. Now this says greater than 22. There is no feasible solution. So we fathom and say infeasible. Good for us. We don't have to do any more. So everything is fathom now. There is nowhere else to branch. So now we see what is the best solution. Which is the best solution? Any of the two, because they have the same value. So it's this point and this point, any one of the two, because if you join the two, that becomes the slope of the objective function. So both of them have the same function value. Okay, so in this process you can actually find multiple solutions, and you have to keep doing it until you fathomed everything. So by the time you fathomed, if there are multiple solutions, they will be there. You can find them simultaneously. So that's a plus point. But you see, even with two variables, how many branches we've got? We've got first problem here we solved, and then 1, 2, 3, 4, 5, 6, 7. 7 problem total we have to solve. So sometimes it can grow. And you see, we started with x2, then we went to x1, and x2 comes back again. Because it depends on what's happening, how the lines are. You have to split like this. So as you have more and more variables, and if they are repeating, then you can be in business for a long time doing this. Okay? But hopefully this gave you an idea of how eventually this process goes and finds integer solutions. Okay? Any question? No? You understood? So then you are going to submit it on tomorrow's class before we start. Yeah. And can you make such a plot? May not be using a software, but by hand. Yeah. You can actually focus only in that region. You can blow up that region and focus and show every step. So what I want you to do is point A. You can mark point A, point B. Here, of course, there is no point. C, D, and E in the figure that you've got. So that way I know that you have understood the whole process of what's happening graphically as well as through this branch and bound process. All right, so if you have no more questions, we'll stop. And tomorrow then I will start genetic algorithms. I was supposed to start today, But I think we are going at the right pace. If anything faster, then you will have difficulty not understanding something. So I'll probably sacrifice some material at the end, but at least whatever we do, let's do it in a way that you understand it. Okay? All right. By the way, tomorrow again we have an exam. Okay? So we are going to keep it whatever we have done yesterday and today for the exam tomorrow. We'll again have 40 minutes of tutorial and then move for the quiz. Okay.